Look at any steel bridge or titanium aerospace frame, and it's hard to imagine they all started exactly the same way, as a volatile, chaotic liquid entirely devoid of structural strength. Yet those massive engineering marvels that society relies upon to build our cities and span our rivers are built from that exact same fragile soup. The precise physical properties of a beam, how much weight it can bear, whether it will snap under tension or last 100 years, are permanently locked in during the brief seconds it takes to transition from a liquid to a solid. You can mix the perfect chemical recipe for an alloy, but if that quick freezing phase goes wrong, the final product will fail. Engineers track this microscopic timeline using a tool called the cooling curve. It lets them predict whether a finished part will hold steady for a century or crack the moment it is put under load. Let's start with a pure liquid metal. If you let it cool and track its temperature over time, you see a smooth, predictable drop. This cooling curve graph tracks that temperature against time. Notice how the temperature drops steadily, right up until the exact moment of freezing. Then the line flatlines. The temperature stops dropping, creating a thermal arrest. Here is why that plateau happens. As atoms lock into a rigid crystal lattice, they release energy known as the latent heat of fusion. This outward release of heat exactly balances the cooling process, holding the internal temperature completely steady until the entire pool is solid. Inside that liquid pool, the solid state actually kicks off through a process called nucleation. Tiny, stable clusters of atoms bind together to form microscopic solid seeds. These clusters grow rapidly along paths of easiest heat extraction, forming highly structured, branching metallic trees called dendrites. Because this energy exchange is mathematically clean, pure metals cool to form predictable, unified internal structures without dangerous weak points. But in the real world of structural engineering, pure metals are rarely used. We mix them into alloys, and mixing elements entirely ruins that perfect, orderly freezing process. This comparative graph shows how an alloy behaves. Instead of a flat thermal arrest, the temperature drops continuously over a sloping range. The metal freezes gradually. As the alloy cools down that slope, the element with the higher melting point solidifies first. That means the chemical makeup of the liquid that's left behind is constantly shifting, changing the freezing temperature along with it. This creates a severe microscopic danger called coring. Because the freeze happens faster than the atoms can evenly distribute, each metallic grain develops a weaker, segregated chemical composition at its outer edges compared to its center. Zoom out from the microscope, and you encounter a massive physical threat caused by the freezing process itself. Liquid metal is less dense than solid metal, so as it freezes, it physically contracts. The outer shell of a casting cools and freezes first, trapping liquid metal inside. As that trapped core eventually turns solid and shrinks, there is no extra liquid to fill the gap, tearing open a massive physical void in the center, known as a shrinkage pipe. Mixing metals turns a simple phase change into a chaotic event. The resulting internal microscopic weak points and massive physical voids directly lead to real-world structural failure. Metallurgists actively fight back against this chaotic freezing timeline. They have to manipulate exactly how and where the metal solidifies to save the part from its own destructive physics. To control the microscopic structure, they use inoculants, microscopic foreign particles introduced to the liquid. These particles force heterogeneous nucleation, providing ready-made surfaces for crystals to grow on, resulting in finer, stronger metal grains. To defeat those massive shrinkage voids, foundries attach sacrificial liquid reservoirs called risers to the mold. These risers stay hot and feed liquid metal into the shrinking gaps, absorbing the internal damage instead of the final part. Engineers physically cheat the natural cooling process. Without those interventions, the metal structures we build would not be safe for human use. There is exactly one natural exception to the messy, sloping alloy freezing process. It is called the eutectic point. At this exact chemical ratio, a mixed alloy bypasses the shifting freezing range and snaps directly into a solid. Because this mixture transforms at a single, sharp temperature, it flows cleanly and perfectly into joints. This natural anomaly is exactly why eutectic alloys have been vital as electrical solder for decades. Every solid metal object you encounter is a frozen record of a microscopic storm. Controlling that brief timeline of solidification is the invisible foundation of modern engineering.